We're going to discuss an external agent, how an external agent can affect an open system. So let's say you have an open system here, which allows interaction with the outside through this cable. There's a person here carrying a rope, and the rope goes around a pulley, and the pulley is attached to a charge, and the charge is being pulled from position number 1 to position number 2. So the direction of motion is upward, and the charge has a value Q, and the charge exists in an electric field E that points downwards. And of course, in this problem, we're ignoring gravity completely. We're just discussing the electric forces in this problem. So what are the total forces acting on this charge as it's being pulled from position 1 to position 2? Well, there's the electric force, because the charge exists in an electric field, and it's positive, so the force is in the same direction as the electric field, downwards. And then there's the external force, which is the force due to the rope or the rod that's attached to the charge, pulling it upwards. So if you want to get the total work, the work due to all the forces, which is integration from 1 to 2 F total dot dr, what is the total force that's acting on the charge during the motion? The total force is F external plus the electric force. And F external here, I put it as a vector. So of course, in this case, it points upwards. And Fe, in this case, of course, it points downwards. But I'm just putting it in general as a vector, both of them as vectors. You add the two vectors. So Fe would be pointing down, F external would be pointing up. And you add these two vectors to get the total force acting on the charge as it's moving. Okay, so now we know that these are the total forces, all the forces acting on the charge. So how can we apply the work kinetic energy theorem? What would the work kinetic energy theorem say in this case? The work kinetic energy theorem says that the work due to all forces is the change in kinetic energy. So it's the kinetic energy at position 2 minus the kinetic energy at position 1. So let's consider the special case where the speed is the same at point 1 and point 2. So for instance, the charge could be at rest here, and then you move it, and then you bring it back to rest here. Or the charge could be at some certain speed, say 5 meters per second, and then you move it, and then you bring it back exactly at 5 meters per second later on. So what would the kinetic energy then be in this case for the initial and final points? They'll be the same exactly. So the change in kinetic energy will be 0. So if there's no change in kinetic energy, then we conclude that the total work done by all forces should be 0. So that means that the work due to the electric field, this part, is the negative of the work due to the external agent, this part, because the sum of the two works is 0, so each one is the negative of the other. And this is only the case when the initial speed is equal to the final speed. So we conclude in this part an important point, which is that the work to go from one position to another position due to an external agent is the negative of the work due to the electric field if the speeds are the same at the initial and final positions. Now this does not mean that the force F, the electric force, is the negative of the external force at every position, at every point along the path. Because for instance, at the initial position, let's say the speed was 0. So if you want to get this charge to gain speed, you need the F external to be bigger than Fe in the first part so that it accelerates and it gains some speed. Once it gains some speed, you can move with a constant speed. And during that part of the motion, then the two forces are equal and opposite. But then when you come to decelerate, because you need to bring it back to 0 speed, then in that case, the Fe should be bigger than F external, so it decelerates to 0 again. So during that part of the motion, the forces are not equal and opposite. So in general, this does not mean that the forces are equal and opposite at every point along the path.